Hello, in the previous clip we saw that if we knew something about the disturbance that is affecting our plant, we can actually do better than a regular controller in rejecting the disturbance, or in a similar manner if we know something about the reference that we are intending to track, then we can do much better than what a conventional controller does. And the tool that allowed us to do it was what we called as the internal model principle. And the central aspect of internal model principle is to include the denominator polynomial of either the disturbance or the reference that we want to reject or track respectively as part of the denominator polynomial of the controller itself. Now, just as we could do a little bit better, in fact we could reject disturbances perfectly in steady state or track references perfectly in steady state if we happen to know their frequency. One would therefore expect that we should be in a position to do better if we happen to know something more about the plant as well. So, for instance, if we have no uncertainty associated with the plant, in other words the plant model is known very well and it is also known not to change significantly with time, then what benefits would accrue as far as control design is concerned? One straightforward benefit is that instead of going from closed loop frequency domain to open loop frequency domain and performing control design using Bode plots or root locus or any of the other techniques and then coming back to the closed loop frequency domain and then looking at the response in the time domain, one can directly synthesize the closed loop transfer function of the overall control system. So, for instance, if we happen to know the plant model P naught of S very well, then we do not really need to go to the open loop frequency domain, but instead directly obtain that controller C of S, which gives us the desired transmission function T equal to C times P naught by 1 plus C times P naught. So, what this therefore allows us to do is, if we happen to know the plant model P naught very well and we also know that this plant model is not changing with time, so it is not having one set of parameters now and another set of parameters some time from now and so on, then we can directly synthesize the transmission function T and find that controller C which gives us this transmission function T. Now, if we rearrange this equation, we would have T times 1 plus C times P naught to be equal to C times P naught, or in other words T is equal to C times P naught times 1 minus T, and this implies therefore that the feedback controller C of S which gives us this transmission function T of S is given by C of S is equal to P naught inverse times T by 1 minus T. So, this simple strategy of synthesizing the feedback controller by assuming that we know what transmission function T of S we already want is called direct design. And what is quite unsurprising here is to note that our controller transfer function C of S has P naught inverse as one of the terms and that multiplies T by 1 minus T. So, in effect therefore, we are cancelling the plant dynamics from the overall feedback loop and replacing it with whatever dynamics we want in the open loop system, so that the closed loop system has the desired transmission function T, because our open loop gain is going to be given by L is equal to C times P naught, and if I were to substitute for C from this equation above, it would be equal to P naught inverse times T by 1 minus T times P naught, and that is essentially equal to T by 1 minus T. So, in the forward path therefore, we have cancelled the plant dynamics altogether and replaced it with whatever dynamics we want to give us the desired transmission function T for the closed loop system. Now, as simple as this technique looks, there are a few caveats. So, for one thing, we want our controller C of S to be physically realizable, and if we choose a transmission function whose relative degree is less than the relative degree of the plant, then we will end up with a controller which is not physically realizable. To see this, all we need to do is look at this equation here. From this equation we see that if nt is the degree of the denominator polynomial and mt is the degree of the numerator polynomial, then the relative degree of the transmission function t is given by nt minus mt. And we see that the degree of the numerator polynomial of t is essentially the sum of the degrees of the numerator polynomial of c and the degree of the numerator polynomial of p naught. Likewise, the degree of the denominator polynomial of t is going to be equal to the sum of the degree of the denominator polynomial of c and the degree of the denominator polynomial of p naught. So therefore nt minus mt is therefore going to be equal to np plus nc, where np and nc are the degrees of the denominator polynomials of the plant and the controller respectively, minus mp plus mc, where mp and mc are the degrees of the numerator polynomials of the plant and the controller respectively. Now we know that each of these systems need to be physically realizable. So nt minus mt is equal to np minus mp plus nc minus mc. Now since each of these systems have to be physically realizable, we want the relative degree of the controller, namely nc minus mc, to be greater than or equal to 0. And what this implies therefore is that nt minus mt, which is the relative degree of the overall closed loop system, should be greater than or equal to np minus mp, which is the relative degree of the plant. Our closed loop transmission function t has to be chosen to be at least a third order transfer function. Likewise, if our plant is a second order system or its relative degree is 2, then we have to choose our transmission function to at least have a relative degree of 2 in order for the controller to be a physically realizable causal controller. Now given this necessary condition for determination of t, we are still left with considerable flexibility and freedom as far as the exact structure of t is concerned. Now how might one want to choose the transmission function t? Now generally, as control engineers, we want the transmission function to be as close to unity over as wide a frequency range as possible. So if I were to plot the magnitude of t as function of frequency omega, we want the transmission function to be as close to 1 and as flat as possible over as wide a frequency range as possible. That will ensure that within the bandwidth of this frequency response, we would have x of t to be equal to r of t, or we would be achieving the ideal of control to the extent that we possibly can. Now of course we cannot get magnitude of t to be equal to 1 for all frequencies. There will have to be a corner frequency omega c at which we should allow for this transmission function to roll off. Why is that so? That is so because if you remember, our controller transfer function c was given by c is equal to p naught inverse times t by 1 minus t. Now how do we obtain p naught? P naught is the plant transfer function, and that has to be obtained from experimental results, and then those experimentally obtained plant transfer function has to be inverted. Now when we experimentally obtain the plant transfer function, we can imagine that when the frequency of excitation to the plant becomes larger and larger, then the response of the plant to excitation at those frequencies correspondingly becomes very small. Therefore at very large frequencies, our plant's response will be buried in measurement noise. Therefore the uncertainty associated with our plant model will be larger at higher frequencies. There is only a certain frequency up to which we know the plant model very well, beyond which we are not very sure about the exact structure of the plant. Therefore, we will not be able to precisely invert the plant dynamics for frequencies beyond that frequency at which our measurement noise starts to dominate over the response of our plant. Hence, there has to be a frequency omega c beyond which we will not be able to properly invert the plant, and therefore we will not be able to exactly get the transmission function that we want. There is one other reason why we need to limit the transmission function's magnitude to unity up to only a certain frequency omega c. That is because as the frequency increases, the plant's gain generally tends to drop. So, P naught of j omega is generally a decreasing function of omega beyond the bandwidth of the plant. What this implies is that if P naught of j omega is a very small number, then P naught inverse will be a very large number. So, therefore, the output of our controller will be a very large magnitude for frequencies that are well beyond the corner frequencies of the plant. And what that in turn implies therefore is that the output of the controller is going to be very large, and that's likely going to saturate our electronics. Hence, for all these reasons, we cannot choose arbitrarily large bandwidths for the overall transmission function. As a rule of thumb, the upper limit could be approximately one order of magnitude beyond the bandwidth of the plant itself. So, that is the best possible bandwidth for the overall transmission function T that one can accomplish, provided we are able to characterize the model of the plant very well up to 1 decade beyond the corner frequency, the bandwidth of the plant. So, ideally we want our transmission function to be 1, but we now realize that it cannot be 1 practically for all frequencies. So, we have chosen to expect our response to be close to 1 up to some frequency omega c. Now, the question is, what should the specific functional form for T of j omega, the overall transmission function, which is going to be equal to c times p by 1 plus c times p of j omega, be between the frequencies 0 and omega c? What should T of j omega look like? Now, since we want T of j omega to be as close to 1 as possible, a good choice for T would be a maximally flat filter, or in other words a Butterworth filter. If we choose the transmission function T to be a Butterworth filter, then we would have a maximally flat magnitude response within the pass band of this filter, and that will allow our filter to have a gain that is as close to 1 as is possible within its pass band. If you look at the transfer function of a Butterworth filter, you would notice that the magnitude of T of j omega, the square, if T of j omega were to have a Butterworth filter's characteristics, would be given by magnitude of T the square is equal to 1 by 1 plus omega by omega c to the power 2n, where n is the order of that filter. So, by choosing an appropriately high order filter, you can get very flat pass band transmission function and a fairly steep roll off after the frequency omega c. This brings us to the end of 1 degree of freedom control design. Thank you.